All right, shall we start? Everyone, please take a seat. Cool, thanks. So, my name is Foivos. It's this little difficult Greek name to pronounce. And I'm going to be presenting to you today a little tool we wrote at Utility Warehouse to basically help us with our cross-cluster communication. We named it after Semaphore, which is inspired by, good old semaphores transferring stuff over distance. So, let me start, excuse me. Let me start by saying a few words about our environment and the problem we're going to deal with. So, in our case, we have multiple different Kubernetes clusters. So when I'm going to say cluster in this little talk, I'm always going to be referring to Kubernetes clusters. And we run them on different places. We have like AWS, GCP, on-premises. And an important thing is that we keep a flat network between all the clusters. That, in other words, means that basically the nodes can speak between each other. And in more plain words, if I'm in cluster A, node 1, I can just ping cluster B node 1, for example. Equally important, we use different distinct pod subnets on each cluster. So if I'm about to deploy something on cluster A, I'm going to be sure that the pods assigned to my deployment are going to get different IPs from some workload that runs on a remote cluster. Now, what's the problem? The problem is that we want to be able to basically to talk pod to pod everywhere. This is too wide of a problem, arguably. So we're going to split it into three sub-problems, and we're going to tackle each of them independently. The first one is how can we route traffic? How can we know about remote pod subnetworks? Because for those of you familiar with Kubernetes, pods run on an overlay network on top of nodes, so we need to make routes on every host in order to be able to talk to pods remotely. And how are we going to be sure that when we send data out, when data is transmitted outside of a data center, how are we going to be sure that this is safe for us? The next one is cross-cluster services. So Kubernetes has this concept of cluster service, which is basically a virtual IP to load balance stuff to an application, to a set of pods that are selected by some label. We want to have a similar mechanism to send traffic to remote workloads, but we don't really want, we already deploy Kubernetes everywhere. We don't want to be spending too much time deploying more stuff outside of those clusters. And finally, we want firewall. So basically, we want to be able to specify rules for who can talk to whom, regardless of where you reside. Now, there are a few considerations here when trying to design a solution. From the user perspective, the user in our case is just a developer or maybe a team of developers, anyone basically that is going to be deploying stuff and using the clusters. There are a lot of solutions out there that are basically implementing service mesh models. This is not going to be one of them. This is completely out of scope here. So we don't care about providing tools for health checking. We don't care for circuit breaking, none of that stuff. We're just concerned on the three tasks on the previous slide. Then ideally, we don't want anyone to change many things in order to use the solution. We want basically, if I have a manifest that I deploy somewhere and it works, I ideally want to be able to keep using the same manifest with minimal changes and send my traffic to something that runs in a different Kubernetes cluster. We played a bit with sidecars, and because Envoy was so hyped as a proxy, and we saw people were using it, we tried it, but it was complex, it was difficult, it wasn't something that we wanted to force to the lap of the people that are actually going to use our clusters. And finally, ideally, we don't want anyone to learn anything new in order to use our solution. And we just want everyone to do their good old style job. Now, from someone that's going to actually deploy and understand how this works, one important thing is to be able to achieve everything in isolation, so to be able to work just with solutions separately. So actually, if I just want to have the solution about firewall, I should be able to deploy this and just use this and just govern the communication between different pods on my clusters, and I should buy into only that, so I don't have to be forced to deploy and use a bunch of stuff that I don't want. Also, I don't want this to be spread on every cluster. I want, ideally, to have the minimum footprint possible on a remote cluster, and for that, we are just going to use a service account on each cluster because we need a role. We need some sort of credentials to be able to watch what happens there and update things locally, but that's all we are going to need. And lastly, but maybe the most important thing, is that we don't want a primary, secondary type of model. So we don't want the control plane of one cluster to be affected if another cluster is down. So obviously, if you have a cluster down, data plane is down there, but we don't want a cluster to suffer. For example, our AWS cluster to suffer just because GCP is down and it was the primary cluster, so it now waits around to talk to it again. Which brings us to designing our solution for this, which is what this presentation is about. So the solution is basically going to be implemented in 3 independent operators that are going to run as separate deployments on all of our clusters. We prefixed everything with Semaphore, which is a word we thought is going to be cool to just name this project that we were developing internally. And there are 3 distinct solutions for the 3 problems. We chose Golang to write everything, and there are a bunch of reasons that everyone uses Go every day, and I guess I don't have to tell you guys here. But the most important is that Kubernetes and Go were tied from day 0 that Kubernetes started. So the tools were out there. They're beautiful client implementations for all the tools that we are going to use here. So in reality, it will require minimal code from our side to solve this. Now, what I'm going to do is that I'm going to go to each separate objective one by one. I'm going to explain a little bit how it works and what someone needs to do in order to use it. And fingers crossed, I'm going to try to run a few live commands in one of our environments to demonstrate this in action. Fair warning, if this doesn't work, I have recorded everything as well, so I'm going to fall back to video, which is way less cooler. So, about routing and encryption, we wrote a small daemon set, which is, as a daemon set, is going to be deployed on all our clusters, on all our nodes, which is, basically, it's nothing more than a WireGuard peer manager. So it is a tool to bring up WireGuard interfaces and manage peers for them. And to do that, it utilizes Kubernetes Nodes. And I'm going to elaborate more on that in a bit. Why did we choose WireGuard as the tool to solve this? First of all, it was super hyped until maybe it still is. So why not? It's fun, right? You always need to get fun on your work. But most importantly, it does solve the issue. It does provide the encryption we need. It does route to different subnets, to different peers, and it's completely agnostic to all our applications, so we don't have to worry about, supporting only certain protocols or anything like that. And the last point here is that it was actually, we use Calico in all of our clusters. We come from way back, so we were always tied with Calico, and WireGuard can actually work very nicely with Calico. So from the user perspective, so the developer that is going to use this, what should they do? The short answer is nothing. The operator should be running everywhere, and it should be doing everything on host level. So it should be creating WireGuard interfaces, it should be managing routes, it should be doing everything under the hood, and we shouldn't be worried at all about how this works. In our case, if, for example, there is, on the left here, we have on AWS a server pod that runs on some IP. If everything is running our daemon set, all we have to do from the client side in order to hit that service would be to know this IP address, so then we can just go ahead and directly curl it. Now, how will this actually work on the, what's actually going to happen under the hood? So this, remember, is a daemon set, so it's going to be running on every host on all our clusters. So every node is going to be running Semaphore WireGuard. And it has a list of tasks that is going to try to do, including bringing up, ensuring that we have WireGuard devices running, configuring the peers, rotating keys. And as I said before, it's going to use annotations on Kubernetes nodes to be able to communicate the details from a local peer to all the remote peers. Now, this slide is a bit overwhelming with all these bullets, so I'm going to try to explain this with shapes and colors. Here on top, we have a cluster in AWS, and we have a single node there. And at the bottom, we have a cluster that runs on GCP, and we have 2 nodes. As you can see, there are distinct pod subnets, so all our pods are going to be assigned IPs from those ranges. Equally, here we're using a host local pod CIDR, so its node is going to be assigned the /24 slice from the whole subnet. So if I deploy something on AWS, it should be under this. On node 1, it should be, the pods should take IP addresses under this range. I'm going to focus only on AWS because there's so much information on these slides, and it's going to be handier. So everything runs our little daemon set. And the first job that it's going to do is that it's going to create a WireGuard interface dedicated for the other clusters. So it is going to bring up a WireGuard device, and it's going to generate public and private keys and configure everything on a host level, and for all our traffic to be routed through there. Next, it's going to get all the information that just generated plus the node IP, and it's going to throw all this stuff on under the Kubernetes nodes annotations over here. This is basically for the rest of the Semaphore WireGuard peers in order to be able to come here, see the information, and identify this peer and configure it locally. Next, we want to route basically the full pod subnet for the remote cluster. We want to route it all from the single WireGuard interface we have on the host. So if I'm running something under AWS Node 1 and I want to hit a pod that's under 10.4, the route is going to be a single one, and it's going to go via the local WireGuard TCP interface. And lastly, it's going to, it's going to watch all nodes everywhere apart from the node that's running, so that it can configure the WireGuard peers. For example, here we're going to pick up 2 peers. Each peer has an endpoint address. I don't know if this works still. Yeah. And the allowed IPs that basically correspond to the pod CIDR of the node, and WireGuard is actually smart enough to know and route things properly. I think the next is the demo. I hope I'm not going to play the video, but you never know. So, this is hopefully it's visible. I can try to make things a little bigger. So, on the top panel on my terminal, I'm going to be running commands on an experimental AWS cluster we have. On the middle one, I'm going to be trying stuff on our GCP cluster, and on the bottom is my cheat sheet, so you don't have to watch me typing. So let's suppose that on AWS we have a namespace called server and a simple, as I told you before, this is going to be a very trivial one, and a simple Nginx deployment. This runs with 2 pods, and have the IP address that you can see. The IP ranges here are going to match the ones that I showed on the example before. And on GCP namespace, we have a client pod. So if I want to be able to curl my service on the other side, as I said, I need to know the IP address, which is not handy, but we'll get to that later. And this should really not go anywhere, because why should it? One is on GCP, the other is on AWS. They shouldn't really know anything about each other. Equally, I can just not curl, but use ncat and just see this timeout, because there's no way to route stuff on to the other side. Now I'm going to try to deploy the daemon set on both places. Okay. That's up and running everywhere, so theoretically, my stuff should be open now, yeah. So, yep, the end result is that I can come to GCP and I can just curl my remote IP address. As I was telling you, this all happens via kubenote annotations. So if you go to AWS cluster, what happened is that the operator went to every host, it created WireGuard interfaces, and it went on and updated these annotations. So the daemon set running on GCP is just watching all the nodes, and it's just picking all the information from the annotations in order to configure the local peers. And that was it for, oh, sorry, the clicker plays the video, I didn't know. That was it for the first objective. Now let's move to the cross-cluster services. Ideally, as we said, we want to have something that is a virtual IP that is known locally and can load balance traffic to all my remote services. And for that, we're going to use a concept that's called service mirroring. We're not actually the first ones to invent that. This is used in many places. I know Linkerd is using this, or at least used to use the same principles here. But anyway, in a nutshell, a mirrored service is basically a service that has the same endpoints as the ones that it's targeting. So it's basically going to be a local service with endpoints that are on remote Kubernetes pods that run somewhere on a different cluster. Why is this useful at all? This is useful because it will allow us to do this, to use the exact same mechanism that we use when we access local services, and it will just allow us to load balance traffic to remote workloads, and everything, all the load balancing is actually going to happen on the local host based on the way we chose to proxy stuff on Kubernetes. So this could be IPVS, it could be IP tables, it could be eBPF, it could be whatever local service mechanism we choose. The controller is called Semaphore Service Mirror and is going to do what I described. This is a single controller. It's not going to be, it's going to be a simple deployment. Now, from the user perspective, all the users need to do is they need to go and label their services in one cluster, and they can expect to access the service that they labeled from all the rest of the clusters. Ideally, we want this to be addressed in a similar manner that we address local services. So a local service in Kubernetes is under the domain cluster.local. Ideally, we want it to be to follow a pattern like that. So service name .namespace.service.cluster.our target cluster. So in the example we're using, for the GCP client to be able to talk to our Nginx service, all it has to do is to go to Nginx server service cluster AWS. Now, the technical bit. As we said, the Semaphore service mirror is going to be a single controller. It's going to run in every cluster and is going to mirror services from a remote to a local. The mirroring is going to happen under a single Semaphore namespace. So for all the services that it can discover remotely that the users requested for them to get a mirror, they are going to appear under Semaphore local namespace. And for each one of them, it's going to literally copy-paste the endpoints locally as well. This is something that we can do for a few reasons. First of all, Kubernetes allows us to create services that don't have any endpoints. They're basically placeholders to get a local IP and have a local service. Then it allows us to basically use endpoints that are outside of the cluster, so there are addresses that Kubernetes doesn't know about, and it's still going to go through the same mechanism to implement and load balance traffic. Now, because, as I said, I'm taking everything from every other cluster and I'm stacking under the same Semaphore mirror namespace, I'm going to, it's possible that we could face a collision on the different service, on the names of the different services that we mirror. Because arguably we can have many namespaces, many teams, and we don't have control over what all the stuff are called. When we're mirroring stuff, there is always a chance for them to collide. That's why we're going to introduce a pattern to name our mirrored services, which is going to be cluster-namespace-a separator-name. Now the separator, which is this ugly 73736T, and it stands for the Czech representation of SSM, and SSM is short for Semaphore Service Mirror, is going to be here in the middle just to guarantee that no one can actually come and override my service from a different namespace. Arguably, we could do the same between cluster and namespace because there is the same danger over there, but because cluster is something that is usually set statically by the cluster admin, there's no such risk there. And here we always have to take account how ugly this looks and the fact that we have actually a 64 characters limit when we are naming Kubernetes services. So in our example, our AWS Nginx service under server namespace is going to be mirrored under our GCP cluster, under our Semaphore namespace, and it's going to have this big, ugly, awful name. Now, again, to make things a bit more visual, on the left, we have our AWS cluster, 2 namespaces, 2 different services deployed there. You can see the pod range and the services range, which are different from the ones on the right side. We have our GCP cluster. And on GCP, we're running our service mirror pod. The service mirror pod is going to watch services on the other side, provided that these are labeled and we want them to be mirrored. And it's going to create here local services under Semaphore namespace, getting a local IP address that corresponds to a service under GCP, but still is going to use the remote pods as endpoints. For this to be a proper mirror, it should always follow what happens on the other side. So for example, if I roll a pod under AWS, this should instantly pick this up and reflect it on my mirrored service. Equally, if I just go and delete service, I don't have any usage for the mirror anymore. Now, this does the mirroring bit, but it's still ugly and very difficult to use and be able and expect people to be able to use those weird long names. So to tackle that, we're going to use something that Core DNS offers us, and it's going to we're basically going to utilize the rewrite plugin, and we want to basically take a name that a client is asking and rewrite it to something that we know we can resolve. So, for example, we don't want to have a query for this big, ugly service. We want to have a query for the simple Nginx server service cluster AWS, because this is something that we can know and predict how it's going to be. Now, for that, we're going to do some regular expression matching and rewriting the queries. So everyone is familiar with regex, so I'm not going to go into much detail about this bit, but the idea here is that we just match we just group the address that was queried by a client, and we just rewrite it to always to the format we expect this to be mirrored locally. Then we can use this one on core DNS, and we can try to resolve it as usual, right? This should or should not resolve on the local cluster if this mirrored service is available. It's important here that when you do that, you need to do the exact opposite operation before replying back to the client, because 9 out of 10 clients, all the same ones, are going to complain that you're giving me a response for something that I didn't ask you, so I'm not going to trust this, I'm not going to accept this. So we should always rewrite the ugly bit to the one that the client asked for. And that will bring us to the second part of the demo. So in here, I've shown that before, but yeah, I have on AWS side, I have my Nginx service and I have my 2 pods, which I want to be able to access from GCP side in a pretty name. So I want to do this on GCP. The GCP is the one that needs to be mirroring services. So I'm going to deploy the Semaphore service mirror just on GCP. This is now ready. Then I should come here and I should label my pod using the label that I need in order to instruct the controller on the remote cluster to mirror this service. Now, if this worked, I should be, sorry. I should be able to just curl the other side using this name nginx. Let me make this bigger again. nginx.server.service.cluster.aws. Equally, my netcat should just work, and more importantly, we should see that this thing actually resolves to a local service. This service is this one, the one that we just expected to be mirrored using this big ugly name. And if we describe the service, we can actually see that this is a service with a GCP service IP, but with endpoints on that actually match our Nginx pods on the top panel. And that was it for mirroring our services. Next on is going to be the firewall. So we now have pod-to-pod connectivity across our clusters. We now have a way to to target remote services. We want to be able to govern which pod can talk to which pod on the other side. Well, no surprise here, another controller that is going to implement and run on all the clusters that need policies. And this is basically how this will work, is that it's going to create and make labels available for us to be able to use them when we define network policies. Ideally, our end goal is to limit access down to specific cluster, namespace, and pods. So I can say only allow access from GCP client namespace, client pod to my server on the other side. Now, from the user perspective, the user now has to come and label his workloads in order to assign policy names. So this policy name is going to go on the deployment that is actually going to request access to somewhere. Additionally, the operator is going to come and make two more labels available. One is going to contain information about namespaces, and the other is going to contain information about the clusters. And all these three labels, they could be potentially used in network policies in order to limit access. So on our usual example, on the left side, I have again my Nginx server service on AWS. On the right side, I have my client. Now, what I need to do as a user is I need to go and label my client and assign a policy name. Let's say, for simplicity, that the policy name is going to be client. Then on the AWS side, I should be able to just define network policies that are that target workloads like that by using my labels. Now, the technical bit. This is massively dependent on Calico. It cannot work if one is not running, is not using Calico CNI on their cluster. And so Calico offers a resource that is named Global Network Set, which is basically a way to group network sets under a local resource. So, sorry. So our controller is going to just be watching the user's policies, and it's going to be creating and updating local network sets that contain all the labels. Because of Calico, again, these network sets, they can be used when we specify network policies. So, for example, again, on the usual trivial use case, my client is going to be assigned a policy named client. This is going to trigger the policy operator on the other side to go and create this global network set. Now, what this set contains is it contains all the labels that are used to filter the traffic, and is going to have 3 nets in this case. Each net is a simple /32, so a single address, and it corresponds to one pod address on the other side. So for this particular scenario, we're going to have 3/32 that are going to be representing these 3 pods that we have, these 3 client pods. And the same thing will happen for every other deployment that we have, which we label and assign a policy. And that's my final demo bit. So for things to work in the first place, we just assume that we have a super open network policy on AWS side. Now what I'm going to do is that I'm going to patch this, and I'm going to limit down access to my AWS pods from traffic coming from my own namespace. If this works correctly, then I should no longer be able to do this. Yeah, because now it's not allowed. Now I'm going to deploy the policy controller, and I want to deploy this on AWS side because this is where I'm going to be creating network policies. This is where the deployment that I care about, who accesses it, lives. All right, this is ready. Next, as I told you, I want to enforce a cross-cluster specific policies, which is going to be this one. It's going to be selecting my local Nginx pod, and it's going to be allowing traffic from my particular GCP deployment. Now, let me apply that. Of course, it's not going to work yet because I am not doing anything on the GCP side. Let's start watching for network sets as well. There's none here so far because we haven't done anything. We tried the curling, so now we're going to try to patch the local application to add a policy named client. This will probably need some time to be rolled. I just chose a stateful set here just to make copy pasting the commands handier. This could equally be a deployment or anything really. Okay, this takes surprisingly long, but I'm well ahead of time here, so that's all right. Yeah, I'm going to, okay, there it goes. Yeah, and actually this is not a good command because it should be showing the pod IPs as well, because as you saw, a network set popped up on the other side that contains a single /32 network, which is my pod's IP here. So next one is try to access, and it goes through. As you remember before, this was not working. Now to make this a bit more clear, let's do a bot client. Let's implement a bot client. The bot client is just going to be the same Alpine simplistic deployment that is not going to be labeled with a particular policy. So if everything works correctly, the bot client does not really have access to my server. Yeah, of course, because it's bad. And yeah, equally we can just try to scale things and just watch what happens. So yeah, the policies, the network sets on the top panel are always going to be updated to always include all my clients' IPs, so I can equally access my service from all the clients down there. And that was pretty much it. A special mention should go out for WireGuard and Calico because these all work and they basically need minimal code because of the nice WireGuard Golang implementation that we used and Calico project, which is something that we use for years now with our Kubernetes clusters. And a little bit about this work. This is we open source everything, even though we appreciate that everything here is just developed to provide a solution based on our stack. There might be other solutions out there, but this was simple and fun enough to work against our stack. And since I'm well ahead of time, we have time for questions. A little bit about myself. I'm an infrastructure architect at Utility Warehouse, and I guess we have time now for any questions, or anyone can feel free to reach to any of us out there. We have a little stand, so feel free to just come and even just say hi.
Thanks. I wasn't expecting a microphone. Yeah, so this might be a naive question, but how did you expose each of the clusters to each other? So I assume that...
Yeah, this is, it was on the first slide. It's kind of a prerequisite for this. So yeah, in our case, this did not handle exposing host IPs from one cluster to the other, right? This was the flat layer 3 network that I talked about. There are different solutions. I know what we use, but it's like, it's how you want to connect or tunnel between the clusters, like depends on where your clusters are and what solution you want to use. So I'm not going to go to more specific than that. But this, yeah, this is, I appreciate this is a prerequisite, and this is like something that needs to be there before you can start talking about all this stuff.
Hi, thanks for the talk. Great stuff. So I'm wondering, what's the overhead on all those pods and resources that it creates using memory, CPU, networking, IP addresses that the pods take in terms of as compared to just having an open policy on the communication side and open endpoints that you can create in policies? Like, what is the benefit in doing either?
Yeah, so I guess this can be answered for all the three components separately, right? So for the routing and everything, the WireGuard is pretty efficient. You're still running WireGuard on every node. You're still peering and sending traffic, do all the handshakes between the nodes. But it shouldn't be very hungry on CPU or anything. Now, regarding the other controllers, the load is really on Kubernetes API servers, right? Because you're constantly watching resources on the remote cluster, so you're constantly querying there. But locally, you just create resources, you just create services, and you just create network sets. The policies are going to be there anyway, because in our case, we're using Calico, right? So you can define network policies. You don't really put any extra load there. The load is on the operators that are single pods, but are watching constantly the remote API servers. Does that answer it? Yeah. Cheers.
Hi there.
Hey.
I wonder if you could help me with the bigger picture. It's a very interesting system, but I wonder if you could talk about why you would use it and give some examples as to where you would use it.
Of course. First of all, for fun, right? It's a fun one. You have clusters, why don't talk between them? But yeah, this was, the example was super trivial, but we can equally deploy data stores that span across different clusters. So in our case, we have done this, we have done, etc. this on all 3 clusters. So theoretically, we are trying to be more resilient. We are trying to make sure that if for some reason, we wanted to push a lot of things on premises, right? But we're not at a place that we trust on-premises cluster that much, and we want to be able to go to end to a place where if clusters goes down, I can just fail over somewhere and I'm not losing any of my data. That's the bigger picture here. That aside, again, it's fun.
Hi, great talk, by the way. I'm just wondering what your strategies are around monitoring. We use something a little bit similar with Istio, and it comes with some really great monitoring tools for some of the network performance. So I'm just wondering what your strategy is around that.
Yeah, fair enough. I didn't add any metrics or any of that on the talk. I was afraid I'm going to become boring. But yeah, we do expose a few metrics, Prometheus metrics. So for the WireGuard stuff, you can have like a complete dashboard that displays the traffic everywhere. We're basically on monitoring because we are using Kubernetes principles. We're most concerned on what fails to talk to what. So we basically monitor our client requests, and if something fails to talk to a remote API server, then we want to alert on that and act on that. If that works fine, we kind of trust that the solution, because it's using native principles from Kubernetes, right? We're kind of trust that everything else is going to be working, because you don't monitor your local network policies, do you? You trust that they're going to work, but so we monitor the controllers, the fact that they can talk to both API servers and create objects. We monitor errors, we monitor all this stuff, but that's as far as we go.
Thank you for the talk. It was really interesting. I was just wondering if you have considered possibly just exposing the kubedns from the other cluster to your other cluster, and then you can maybe just modify the resolve.conf files inside each pod to basically query the DNS of the other cluster instead of just mirroring everything between clusters.
Yes, we did, but yeah, this concerns services, right? We did, but in order to hit a Kubernetes service, you basically need all the load balancing happens on the host, right? It depends on what are you using to proxy your stuff. So in our case, we use IPVS. So it's not enough that we can figure out the address from something remote. We need Kubernetes to actually implement the service on the host. So that's why we needed the local service here, because when you go when you go back here, if you want to if you want to access the service 10.5.20.100 on your on a pod running on GCP, load balancing is going to happen on the host. It's on the host that the pod is running, actually. So, and this is all set by Kubernetes. So, what's going to happen is that it's going to go to, in our case, we use IPVS. It's going to go to the IPVS table and it's going to select to round robin to one of the 3 addresses. And this is all set up by Kubernetes. So, it's not enough. If we made this IP available over there, we would still not be able to use it at all. Does that make sense? All right, I guess that's it. Thank you. Cheers.